For the rest of this lecture, I'm going to introduce different types of radiometric correction. So, so the purpose of radiometric correction is to improve the accuracy of surface spectral reflectance, emittance, or backscattered measurements obtained using a remote sensing system, because there is always errors. These errors could be from the remote sensing system itself. So this type of errors are considered internal errors or sensor errors, okay, introduced by the remote sensing system itself. Because, you know, sensor is nothing but a scientific product or a research product. It's an item. It's a hardware. It's hardware. So it's possible that it's poorly designed, not very well designed, or it has been serving for too long, or there could be random error in itself, in a sensor itself. Those errors could be leading to errors in your images, in images collected by this sensor, right? So this type of error is from the remote sensing itself. It's also called a systematic error, and it's predictable, right? Even a sensor is in the sky, the satellite is in the sky, we can still control it from ground stations, which means that we can see, we can detect, we know that there is error, and maybe from a ground station, we know that the sensor is not working very well in the sky. So it's predictable, it's detectable. It's not that random. There could be random internal errors, but compared to external errors, they are relatively predictable. Okay, external errors, they are from phenomena that vary in nature through space and time. For example, at the very beginning of this lecture, I introduced the travel of EMR through Earth's atmosphere, right? So it's a very complex process, and EMR interacts with different materials, particles in Earth's atmosphere. This process cannot be controlled. Okay, so it's relatively random, and it's not from the remote sensing system itself. So we call this type of errors external errors, because they are introduced by something outside the remote sensing system. Okay, so let's talk about sensor correction first. It's a type of radiometric correction because there could be errors introduced by sensors. So correct sensor errors when the individual detectors do not function properly. So usually calibrated at the satellite ground stations. Okay. Common sensor errors include random bad pixel, line column dropouts, line start problem, inline stripping problem. Let me introduce them one by one. So firstly, say here we have an image. We have an image, and we zoom in to focus on this specific area within this white square. Okay, so we can say there are two bad pixels. They are black. Okay, you may ask why you know they are bad pixels, because if you check their surroundings, all other surrounding pixels, they have a specific grayscale instead of pure black. It's not likely to happen in real world. For example, this is an urbanized area, or this is agriculture area, and suddenly there is something very different in terms of reflectance appearing in the middle of this land cover type. It's not possible. So these two pixels, these two pure black pixels, or we can say pixels with zero reflectance, or simply bad pixels, they need to be addressed. Okay, on the right side we have the same image after sensor correction. So how did I do that? It's very simple. We open a window which covers a bad pixel and make that bad pixel the central pixel of this window. So here is a window, okay? It's a 3 by 3 pixel window. So I is used to address what? Row number. J is used to address column number. So the central pixel BVIJK is the bad pixel, okay? So there are how many? 1, 2, 3, 4, 5, 6, 7, 8, 8 surrounding pixels. Since the middle pixel is a bad pixel, you can do nothing. I mean, you can do nothing about it in terms of collecting data again. It's not possible. Okay, the image has been taken. It's a bad pixel. You can do nothing about it. But you can calculate the average value of its surrounding pixels. For example, the brightness value of surrounding pixels, they are normal pixels. You add them up and divide that value by 8. Why 8? Because there are 8 surrounding pixels. You simply calculate the average value of surrounding pixels and assign that average value to that bad pixel in the center of this window. You may say, okay, it's not the actual value of that pixel, right? You are correct. But this is a compromise. Since that pixel, the central pixel is bad, there is no value from that pixel. So this is a compromise. Okay, this is what we usually do. This is also called an average filter. Okay, you calculate the average value and assign that value to the central pixel. Done. Okay, so this is the most straightforward way to deal with random bad pixels. Okay, it can also be called as spatial averaging or spatial smoothing. Spatial smoothing is not that accurate because we have different types of methods for spatial smoothing, but spatial averaging is very accurate. Okay, it's very accurate. And the second type of sensor error is this. It's called line or column dropout. So we can say, obviously, there are 4 abnormal lines here. They have extremely high value because they are purely white. So it occurs when a detector completely fails to function or becomes temporarily saturated during a scan. You know that it's not possible, right? We have 4 straight lines with pixels who have saturated value, highest value. It's not possible. It's an error. So result in a brightness value of 0 or 255. So obviously for this specific image, all those pixels, they have a value of 255 because they're purely white, right? If they had a value of 0, they should be all dark. So for every pixel, in a particular line and a particular band, okay, this line appears black or bright, okay, and it is estimated. We need to use estimated brightness values for each bad line to fix this error. Again, what's done is done. You cannot collect the true reflectance of these values on these lines anymore. So again, you need to use something like this spatial averaging filter to assign values to these pixels, to these bad pixels along these lines. So here, again, it's very simple. Okay, so BVI minus 1 is used to, for example, for this specific line, okay, this top line, okay, each pixel along on this line has a neighbor on the top of it and has a neighbor below it. We simply use the average value of these 2 pixels, one below it, one above it. We add them up, we add their values up and divide that result by 2, which means that after this correction, each pixel along these lines has an average value of its 2 neighbors, one neighbor above it, one neighbor below it. Okay, so this is just another type of spatial averaging, but this time it's not all these pixels surrounding each pixel. It's just the pixel above it and the pixel below it. Because here, obviously, you cannot use all pixels surrounding each bad pixel to do the spatial averaging. You simply use the one above it and below it. The int here means integer. So it means that when you have an average value, we only want the integer part of that value because BV value, brightness value is always an integer. Okay. So third type of error, sensor error here is called line start problem. So on the left side, we can say here is a river and there is a stream converging into this river, and this stream for some reason its brightness value, the general brightness value is higher than this huge river because it's brighter, right? But yeah, that is not the problem here. The problem is that if you observe this part of the river, you can see the shape of the river is distorted, because obviously if this image is normal, this whole part should be occupied by how can I say naturally distributed bright pixels. But here you can say some dark pixels, they should not be here because this is the boundary of the river. These gray pixels, they're invading this river. You know, it's not possible in the real world, right? And suddenly there is a part of soil invading this river. It's not possible. And here you can say, right, some gray pixels, they are invading this part of the image. It's distorted. That's because they are 1 pixel right. Let me say this. How can I say this? I mean, there are several lines there. Okay, and along these lines, all the pixels along the several skylines, they are what? 1 right pixel. 1 pixel right from their correct positions. Okay, so what do? You simply find out those lines and move all these lines to the left by 1 pixel. So these bad pixels, these pixels with problems, with position problem, could go back to their original position, to their correct position, just like this. Okay, so we have at least 1, 2, 3, 4, 5, 6, 7 lines have this line start problem. Okay, so they're 1 pixel right to their correct position. So we just move them left by 1 pixel. Okay, so if you compare the left image and the right image, obviously the right image looks better than the left one because all those distortions here, they disappeared because you moved all those lines with problems 1 pixel left. So you would say, how about this empty pixels here? They are problems now. I have to say, you can do nothing about that. Obviously, you can do spatial averaging like we did before for single or bad pixels along lines. You can do that, or if you don't use the boundary of the image, you can simply ignore them. Okay, so this is line start problem. Okay, the detectors, some detectors, they started from can I say, if all detectors they started to scan the same area simultaneously, there shouldn't be this line start problems. Some detectors they started late, okay, than other detectors. So that's the reason why there is a spatial error of 1 pixel. All those sensors responsible for the several lines, they started late, okay, or they started earlier than they should be. So here is a problem, okay. Okay, the next problem here, the next type of error from sensors is called line stripping. So it occurs if a detector goes out of adjustment. It provides readings consistently greater than or less than the other detectors for the same band over the same ground cover. So here is an example. Here is an example. On the left side, it's a Landsat TM band 3 data of a specific area, If you check this image, there are strips. For example, here is one, right? Here is another one. And there are a lot of strips, horizontal strips. It means that some sensors, they lack adjustment, radiometric adjustment. The result is that they always collect, how can I say that? Collect information, or you can say the pixels detected by these sensors, they always have relatively higher values than they should be, than they should have. Okay, so that's the reason why you can use your eyes to say that obviously there are some lines here, they are brighter than their neighbors. Okay, so in order to do that, in order to de-strip all those strips, of course, and you need to use different methods. The most commonly used method is spatial filtering. Okay, I have introduced a spatial averaging, right? That's a type of spatial filtering, but there are even more complex ones. Okay, so you don't have to, we don't have to go deep for specific methods here because this class is not about image processing. But here you just need to know that there is something called de-stripping. Okay, the problem is called inline stripping. So we use these stripping methods to address it. Okay, here is a more obvious example, clear example. So this is an image before de-stripping. If you zoom in, you can see all those strips. Okay, they're brighter than their surrounding neighbors, right? After de-stripping, this is the image itself. And if you zoom in, I mean, it's better than before, but here you can still say that, how can I say, you can still see some strips, but still it's better than the original one. Okay, if you compare these two images. So inline stripping and de-stripping. Okay, next type of radiometric correction is called atmospheric correction. And there are two types of them. The first type is called absolute radiometric correction of atmospheric attenuation. Okay, so we use something called radiative transfer models. Okay, or radiative transfer modeling to address the transmission of EMR in Earth's atmosphere, which means that what? We need to know the mechanism of atmospheric attenuation, or we need to know the mechanism or the interaction between EMR and all those materials, particles in the atmosphere. So this is called radiative transfer modeling. It's based on rationale. Okay, these models, they're rationale models. And the next type of absolute radiometric correction of atmospheric attenuation is called empirical line calibration. So this is called an empirical model instead of a rationale model because we don't have to address the transmittance of EMR in atmosphere. We only create empirical relationships between the value collected by sensors and the true value, or the value without the interference of atmosphere. Once this empirical relationship is established, we use these empirical models for multiple images, and we don't need to know how EMR and atmosphere interacts. But if you are using radiative transfer models, you need to know how the interactions happen. That's actually the purpose of radiative transfer model. Okay, they tell you how the interactions go, how the interactions happen. And we also have relative radiometric correction of atmospheric attenuation. We use a single image normalization, okay, through histogram adjustment, histogram of pixel values, okay, in an image. Or we can use multiple date image normalization using regression methods, okay? I'm going to introduce them one by one. But before that, let's talk about the interaction between EMR and the atmosphere, Earth's atmosphere. So usually there are 5 paths of EMR when they travel through atmosphere. So the path 1 is here, okay? Path 1, path 2, path 3, path 4, path 5, okay? And you can see here on the right side, this surface is the study area, is the area we care. And on the left side, it's a neighboring area, but it's not the area we care. So the information from this part, from this surface, is distracting, is useless. We do not want it. But you will know that it's not possible to perfectly eliminate the information from this neighboring area from the data you collect from with your sensors. So path 1, so this one, path 1, okay? Path 1 contains spectral solar irradiance that was attenuated very little before illuminating the terrain within the IFO wave. Okay, so path 1 is energy travels through the atmosphere and it was barely affected by the atmosphere. It safely arrives, relatively, okay, safely arrives at the area of interest. And then what? Reflected by this area, okay? Path 2 is here. Path 2 is here. Contains spectral diffuse sky irradiance that never even reaches the Earth's surface because of scattering in the atmosphere. So you can say here is another light, say that, or EMR. It interacts with the atmosphere, and path 2 addresses the energy that never arrives at the ground. Path 2 represents the EMR scattered by atmosphere. So obviously, it's noise. We don't want it because it doesn't have any information about the surface of interest, area of interest. So path 2 is something we want to eliminate, okay? Path 3 contains energy from the sun that has undergone some scattering and perhaps some absorption and re-emission before illuminating the study area. So here is path 3. It contains the EMR scattered by the atmosphere, but luckily it arrives at the surface of the Earth within the study area. And yes, when this part of the EMR is reflected, it contains useful information about the study area. Path 4, okay? Path 4 contains radiation that was reflected or scattered by nearby terrain into the IFO wave of the sensor system. I here is for instant, okay? And path 4 is also useless because it is reflected by a specific surface outside our study area. So it contains the information of the surface object, but that object is not something we care because this area is outside the study area. Path 5 is energy that was also reflected from nearby terrain into the atmosphere, but then scattered or reflected onto the study area. So you can say some energy, some EMR is reflected by the neighboring area. And again, after that, they reaches the study area and reflected by study area. So path 5, energy from path 5 is also something we do not want. And you can say that the reflected energy from area of interest or from study area contains energy from path 1, okay? Energy from path 3, energy from path 5. Okay, so it's very complex, and no need to say that there is also path 4. Path 4 is the reflected energy from neighboring area. So you can say that it's very hard to retrieve the useful information, reflected information for the study area because there are so many factors affecting the energy collected by your camera, by your sensor. Okay, that's the reason why we need atmospheric correction. We want to know the real, the true reflectance of the study area. But there are so many, so many factors could affect the reflected energy collected by your sensor. Okay? Okay, I will stop here and I will see you in the next video for more atmospheric correction. Okay, thank you.